Okay, welcome to this 15th lecture of this course. Here we are going to talk about the symmetry factors. In the last discussion class, some of you said that this symmetry factor was not properly discussed in previous course. So here I'm going to do a bit detailed, structured stuff about the symmetry factors. So why we consider symmetry factor and what is the origin of the symmetry factor will become more apparent and clear when we talk about drawing these diagrams, loop diagrams and higher order diagrams in lambda 5/4 theory. So just for completeness, so here let me write today symmetry factors is what we are going to discuss. Okay, so my Lagrangian density is 1/2 del mu phi minus 1/2 m square phi square minus lambda by 4 factorial, not 41, it is 4 factorial pi to the power 4. Okay, so we see lambda by 4 factorial is the coupling over here, and the choice of the denominator 4 factorial will become obvious. Why we choose this is because we want our Feynman rules, eventual Feynman rules, to be simple and not having some weird constants hanging around. So we'll start with this example, and then we say, okay, let me ask all to as many orders as possible to draw all the relevant diagram possible for phi in Heisenberg picture x1, phi, x2 in Heisenberg picture. This is interacting vacuum, and we know it's a ratio of 2 terms. Okay, so the numerator, okay, we will expand, and we'll also expand the denominator. We will show several stuff, but let's write the numerator of this guy. Okay, so numerator of this, okay, we'll have this first term will be time order product of phi x1 phi x2. Okay, this is what we discussed, and that leads to a simple diagram between x and y, x1 and x2. Okay, then I have plus, and then I have minus I lambda by 4 factorial. This is the first order correction to this thing. Maybe I should move out of this here. D4z, right? So phi of x1, phi of x2, and then phi of z to the power 4 is sitting over here. Okay, now question is, how do I deal with this diagram? Okay, so and what kind of contribution will it give me? So I have to have, so there are several ways to do this particular diagram. So I will say I'm writing numerator of this, but this is not all of the numerator, and let me just say second order term I'm not considering right now. Okay, so what is this diagrammatically in terms of all possible contractions and all these things? Okay, so you see there are 6 fields over here, one of them at x1, another one is x2, and 4 of them is at z. So when it comes to time ordering, but it really doesn't matter how to order this 4 because all of them are at the same time. Okay, so when it comes to all pairwise contractions, okay, I can say I have sorry, while I'm here, let me say that this yellow box diagram, that all the expression for this yellow box, okay, just the diagram level, what I have that x1, x2, I should say at the level of propagators, which propagators and which contractions it. So here I'm only listing the contractions, okay, the factors and all the integrals are still hanging around, and then this 4 of the 5's will multiply with each other. Okay, this is what will going to happen. So question is, how many ways I can get this particular diagram? So x1 is contracted with x2, there's only one way, so fine, I can find the first piece in only one way. Now how many ways I can find this particular diagram when I'm doing pairwise contraction, okay, of the second guy? So you can see I can have exactly same expressions because it's all going from one to another. In it's like how many ways you can contract this? You can contract it like you choose 2 pairs, right? So just a moment. Okay, I'm back. So here okay, so here you wanted to check the factor. So x1 and x2 can be contracted exactly in one ways, but when it comes to 4 of the z contracting into this shape, this infinity shape or 8 shape, whichever you say, then the thing is that how many ways I can connect them. So let's say I choose a guy, okay, and it has to connect with 3 other guys. It can connect with any of the 3 other guys. So basically it can connect only in 3 ways. So it can, like, you know, if you have phi of z, phi of z, phi of z, phi of z, so this contracts with any one of this guy, let's say this one, so in 3 different ways. And once this is contracted, that last 2 has to contract with each other. Okay, so this contraction is 3 different ways. So I have basically, if you give me a string of 4 of these guys, okay, I can contract in 3 different ways, giving me exactly the same guy. Okay, so this gives me a factor of 3, okay, coming from here. But you see from outside I do have, this is z by the way, okay, from outside I have this minus I lambda by 24, okay, and d4 z is sitting over there, okay, multiplying this guy. So times 3 is a factor over here, okay. So and another term, another kind of diagram would be there where x is connected, x1 is connected to one of the z, okay. So let's just say this is the x1 is connected to, here it is z, and here is x2. X1 is connected to one of the z, x2 is connected to another of z, and other 2 are connected to each other. So how many ways this is possible? So it's like I have 4 empty places here, and x1 has to go to any one of them. So that x1 connecting to z can happen in 4 different ways, okay. x2 connecting to, say, rest of the 3 can happen in 3 different ways. So this guy can come in 12 different ways, okay. And in the front I have minus I lambda by 24 d4 z, okay. This guy is there plus, so this is what this yellow box corresponds to. So I have this extra factor. So here when I'm drawing the diagram, I'm only drawing the propagators. So actually the in Feynman diagram, this factors has to be included. That's what the symmetry factor I was coming to, okay. And so this is a couple of examples that you can see. And now let's go to slightly more complicated example, okay. And so because I only have this first order thing, So okay, so let me simplify this. So my yellow box that is there is equal to minus I lambda, okay, in the first diagram divide by 8, and then I have D4Z, then I have this x1 x2 z, okay, where each line you write the propagator. That's the only rule right now here, okay, plus minus I lambda by 2 in the second piece because 12 is here, d4z okay, and here is x1 x2 and z. This is how I'll do the computation. Now let's talk about second order term. So what that looks like in the second order term is first of 1 by 2 factorial because it's exponential term, and minus I lambda by 4 factorial square, okay, and then I have d4z1 d4z2 and vacuum expectation value of time ordered product of phi of x1 phi of x2 then phi of z1 to the power 4 phi of z2 to the power 4. This is what I need to compute. So there are so many ways I can do this, okay, and I don't want to go into all of them. Let me look at the diagrams that one will actually look at later, okay. So the diagram that I'm interested in, and I will ask how many ways it can be computed, is of this kind. X1 is, let's just say, connected to one of the vertex. There is a second vertex. This is x2, and these guys are further connected. This is the diagram. And note it why I'm not committing to the name of the vertex, because z1 and z2, or just write it z1 z2, and here is d4 z1 d4 z2 minus I lambda by factorial 4 square 1 by 2 factorial, okay. There is a diagram like this, plus 1 by 2 factorial minus I lambda by 4 factorial square, and I have d4 z1 d4 z2 of exactly same looking diagram, okay, x1 x2 z2 z1. The only difference between these two things that I wrote is I swap the vertices and they will give me exactly the same thing. So the number of vertices that I have inserted, I can swap them, and in many of the cases they basically give you the same results, okay. So this factorial n, so in this case, since it's the second order, is factor 1 by factorial 2 is there, so I can actually permute this and all the vertices, since they are the coordinates are integrated out anyway, they should give same results in most of the cases. So that is an overcounting, and not overcounting, that's multiple repetition in the all possible contraction that happens, that will actually tend to cancel this 2 factorials over here, okay. So basically I can just say 2 times one of the diagram, and the factorial 2 simply disappears. Now let's look at it how many ways I can do this. Okay, so one thing I already said that to get to this diagram, I'm saying x1 is contracted with z1. Okay, it could have been contracted with z2, which is the second piece. Okay, but since I'm writing them separately and naming them exactly, then I'm asking this question, how many ways this thing can happen. So I could connect x1 with z1 in 4 ways. Okay, I could connect x2 with z2 in 4 ways. Then leftover z1s and leftover z2 have to contract with each other. Okay, and that can be contracted in factorial 3 ways. Why? Because 3 of this left hand z1 fields has to match up with 3 of the z2 fields. So it's like putting 3 objects in 3 boxes, and there are factorial 3 ways to do it. Okay, so 3 factorial. So this is the multiplicity factor over here coming for a given diagram without considering the swap of the vertices, and swap of the vertices is easy to compute. So if I include the swap of the vertex and these factors, so let me just write factor 2 from the vertices. Okay, and these are from the various way you can choose the fields. Okay, so this is the total factor, and these 2 diagrams are same. Okay, so okay, you can't write the 2 diagrams and also talk about the swappings. So since I'm writing the 2 diagrams, I'm not talking about the swappings. So let's focus on one of the diagrams without the factor 2. So I have minus I lambda by 4 factorial square d4 z1 d4 z2, and this factor, which is 4 factorial times 4 times this diagram. Okay, x1 x2 and z1 z2. Okay, the swap thing will give me the same result, so that's why 1 by 2 factorial I did not keep. Okay, so this can again be written as in the following way: the 1 factorial 4 1 factorial 4 cancels out, one of the 4 cancels the 4 in another guy, and it gives me 1 by 3 factorial. Okay, and then I have minus I lambda d4 z1 minus I lambda d4 z2 and x1 z1 z2 x2. Okay, here diagram means each line is representing a propagator and nothing else. Okay, all the factors I am explicitly writing. Okay, I am trying to basically reach towards the Feynman rules. But if you remember the Feynman rules for this guy, it never said that whenever you see a vertex, put minus I lambda by factorial 4. It always said put this factor. Okay, that's what I'm isolating. In the previous diagram also, okay, basically I'm isolating. Okay, I actually wrote by 8 here itself. So basically consider isolating this factor. Okay, so here 1 by 8 and 1 by 2 are the symmetry factors. In this particular case, 1 by 3 factorial is symmetry factor. So what is the symmetry factor? Is because I'm doing certain computation already in while drawing the Feynman diagrams. Okay, so let's go. Okay, so here, since all the diagrams that we are interested in have symmetry factors, non-trivial symmetry factors, let's look at least one diagram and one kind of case, okay, which is the 4-point Green's function. So I'm looking at time order product of phi of x1, phi of x2, phi of x3, phi of x4. Okay, just vacuum expectation value, and one of these terms that you will have is this contains, sorry, time order product of phi So these are all Heisenberg picture, and here ordinary one. So x1, phi x2, phi x3, phi x4. At first order it will have phi z to the power 4. Okay, and since I did not have space to write other stuff, let me write it here. So minus I lambda by 4 factorial d4z. Okay, this is the guy. Now I can do contractions in various ways, but I just looking for a diagram where all of these external phi's contract with the vertex. So it's like putting 4 objects into the 4 boxes, and there are factorial 4 ways of doing it. Okay, so I will have minus I lambda by 4 factorial d4z These are just the propagators you have to write. 1, 2, 3, 4 and z times 4 factorial, because I can put, so x1 can be connected in 4 ways, x2 can be connected in 3 ways, x3 can be connected in just over 2 ways, and x4 now has left only 1. So factorial 4 ways it can be connected in this way. And this factorial 4 and this factorial 4 cancels out. Actually, this is what usually we do. So to simplify our Feynman rules, what we say, okay, is that in lambda by 4 factorial phi to the power 4 as 4 identical fields, okay, leading to typically factorial 4 identical contractions. Even if you name this guy 5 1 5 2 5 3 5 4, you contract in any which way, it has a given expression. Now you do all 24 permutations, okay, changing which leg of this 4 vertex has connected to some what doesn't mean anything, because all of these 4 phi's are identical. So I can permute them, okay, and I can generate 24 different diagrams, and that 24 and the factorial 4 over here, which is 24, cancels. Okay, so this basically says the 1 by factorial 4 in the coupling cancels. This leads to a Feynman rule. Vertex, okay, is usually given by minus I lambda d4z. That's what you write for each vertex. Okay, so that's the first simplification I do. And 2 is for nth order term 1 by n factor in the Taylor series when I'm expanding the exponential, cancel with the n factorial permutations of the identical vertex. Okay, so this is what we basically did in here. So here z1 and z2 are identical vertex. Okay, I can swap them. Okay, so I could swap them or so to say, so but to create this to make this life simpler, because that's what cancels this root 2. But when I did swapping, I did not, in this particular example, it should have cancelled all those factors. So yes, this swapping of these two guys cancel this factor, root 1 by 2 factorial. But when I'm doing replacing this single vertex lambda factorial 4, I just removing it, saying that I can do this thing in factorial 4 ways, and I can do this thing in factorial 4 ways. For this particular diagram, those were not separate stuff. Here I ended up overcounting. If I use this simplifying rules, that you just forget about the factorial 4 because you are going to permute this guy so many times only, so many times anyways. But here all those permutation actually does not give me a separate diagram. Okay, are not independent because I can permute only one side. I can't do the permutation on both sides. So here I am overcounting by a factor of 3 factorial. So okay, so that is the overcounting thing that hangs around. So if I use the usual Feynman rules to write the diagram expression for this diagram, I will write exactly this, and that particular thing, this particular thing is an overestimate by a factor of 6. So I have to divide this by this. Okay, so the way I say got this, that if this was a given diagram, I'll write all the propagators blah blah blah, and I'll write minus I lambda, not by factorial 4, not by factorial 4 here. Okay, so I just wrote it like this, and this is an overestimate. Here there's no overestimate because this is the reason why we invented the rule 1 over here. Okay, and why we wanted to swap the vertices is what we saw in this particular expression. But this overcounting, okay, this leads to an overcounting in symmetric diagrams, and that's why we need to compute this symmetry factor by which it is overcounting. Okay, and then divide whatever the Feynman rules give, divide that thing by the symmetry factor. Okay, so this says need to compute this factor and divide the expression by it. Okay, this is actually one of the rule, is that you have to divide by the symmetry factor. Now when I say it's a symmetric thing, okay, what were the symmetries? Now here, this diagram is symmetric if I exchange these 3 propagator. Exchange means take any 2 propagator and swap them. Okay, so since I draw it and I could have colored it or labeled it differently, and swapping them doesn't change the expression. Okay, because it's all connecting between Z1 to Z2, all 3 of them. So this is a symmetry of this diagram. Okay, and what is the symmetry factor over here? So how many ways I can do this? I can do it in factorial 3 ways. I can permute them in factorial 3 ways, and this is exactly why the factorial 3 is the symmetry factor over here. Okay, let's look at this simple diagram over here. Is there any thing that that it gives me symmetry? So one has to ask symmetry under what? Okay, so this here already we found one rule, that symmetry under swapping of the propagator between the 2 vertex. So if between the 2 vertex there are more than one propagator of the same kind, I must say here all propagator are the scalar propagator. So if they are of same kind, I can permute them among themselves, and that gives me symmetry, and I have to divide by the symmetry diagram. So permute all the propagators between a pair of vertices. So I could ask the same rule here, and the pair of vertices, I could say, okay, swap all the propagators. So this is one propagator and this is another propagator between the same vertex, so I can swap them. There are 2 of them, so here factor 2 will come. Okay, so I need to explain where this 8 comes from. So one factor 2 comes from the fact that I have these 2 propagator that can be exchanged with each other. Another set of rules that will come is what happens when I exchange the 2 ends. Okay, 2 ends of the propagator. So here if whenever a propagator starts and ends, okay, on the same vertex, okay, then that gives me additional factor. So here I have total factor is factor 2 coming from the exchanging the two ends of this lower lobe, factor 2 from the upper lobe, and the factor 2 by exchanging those two propagator itself. So 2 times 2 times 2 is 8 is the factor sitting over here in this. Now here the factor 2 is only sitting there. So where this factor 2 comes is by exchanging the two sides, two ends of this propagator. Now there is, like, if between any two pair of vertex there is only one propagator, so there is no other need to do this. Okay, and so these are the two things I figured out how to find the symmetry factor. Okay, so find symmetry factor is first thing. Permute identical identical propagator. Permute identical propagators between two vertices. Okay, second thing, exchange two ends of the propagator. And there is a third rule, permute identical vertices. Now what do you mean by identical vertices? Identical vertices in a sense that they have exactly identical connections. Example is here. So this is your x1, this is your x2, okay, and here is a vertex, and then this is connected to this vertex, this is connected to this vertex, and there are these legs. So this particular vertex and this particular vertex, they're exactly identical in its connections. Okay, so three of them are connecting to each other, and then how they are connecting to rest of the, so when you say connection, so you have to say connection with regard to all other vertices. Okay, so if I swap these two vertices, it will look the same. The diagram, expressions, everything will look the same. Okay, so that's, so if I have to find the symmetry factor of this guy, okay, so first say permute identical propagators. So I have 1, 2, 3. These are the identical propagators between these two pair of vertex. Okay, so if I choose these two pair of vertex, there are 3 guys, so 3 factorial. Now let's choose x1 and this. Okay, there is no propagator between them, so I can't choose. So let's choose only connectors. So x1 and this, there is only one propagator. This and x2, only one propagator. This and this guy, only one propagator. This and this guy, only one propagator. And between these two, there are 3 propagators, so 3 factorial. Okay. Rule 2, which is exchange the two ends of the propagator. So if I exchange the two ends of this propagator, it's not the same propagator. Same here, same here, same here, same for all of them. Okay, so that doesn't give me anything. Then the third one says permute identical vertices. So these two vertices are identical. Okay, if they were labeled differently, the expressions would not be same. So that will give me 2. So this is 12 is the symmetry factor. So I have to divide the expression of whatever expression of this diagram I will get, I have to divide it by 12. Okay, so, and that is coming from the symmetries basically. So this is how you basically, this is a set of 3 rules you use to compute the symmetry of the diagram. Okay, and I think that's all I have to say about the symmetries. Okay, so basically the philosophy of the symmetry factor you can just take home is that you first do a simplifying thing in your Feynman rules that instead of writing the factorial 4 over here, it says anyway there are going to be 4 factorial ways to permute them, so let me already pre-cancel them. And another thing is that 1 by n factorial that comes in the Taylor series, and they can also be cancelled by permuting the identical vertices, so cancel them. Okay, so but here when I say cancel them is because we are assuming that they lead to a different diagrams with the same expressions, and hence we kind of cancel them and says count them all in because they are giving eventually the same expression. But in this desire for simplification, if we have a symmetric diagrams which are symmetric anyway, so they get over counted by their symmetry factor, and this is how we compute their symmetry factor to divide it to get the ratios right. Although so this might look a complicated exercise, and in my opinion this is unnecessary, because if you do the computation ab initio in a mechanized manner, it is time taking and all that. But what happens what I mean that do all possible contraction in Wick's theorem. So since the all possible contractions and these things can be in principle automated, I'll rather do that and get these factors out, okay, because that is a difficult task, it might appear, but that is still better, because what you are asked to do over here in Feynman rules is first draw the Feynman diagrams and then use the Feynman rules to convert them into an expression. And one of the rule of the converting into expression is that compute the symmetry factors. So first draw the diagram, which is a non-trivial task, and then compute the symmetry factor, which also turns out to be slightly non-trivial task. And it would have been nice that in one go one could do all these things. When we study the functional methods, we will come across a method where using functional derivatives all these things can be obtained. But here the segregation into the diagrams one has to do manually. Or manually I should say, like even when if you use a computer algebra packages, it can do it very nicely. Okay, so like all the terms which look identical to be combined, and all the symmetry factors will come out systematically from there. So we'll do that over there. Next here in this lecture we discuss how do we show, at least just by drawing the diagrams and getting roughly the symmetry, writing the symmetry factors over there. Maybe I will not write the symmetry factors, just draw the diagrams and assume that symmetry factors are already included, and show certain cancellations that has been talked about in Kaushik Datta's lecture in previous course, but I would like to emphasize that part slightly a bit. Yeah, but before I go to that part, I would like to emphasize one more thing over here. So here we had lambda by factorial 4, phi to the power 4. Now if I have a term like lambda phi dagger phi square, okay, so here all phi's appearing over here are not identical. There are 2 phi's and 2 phi daggers, different objects. Okay, so what should be the permutation factors over here that we automatically cancel? So here I would say that there are 2 phi daggers that can give me permutation factor of 2, and 2 phi's that give me permutation factor of 2. So 2 times 2, 4 would be the factor over here, not factorial 4. Okay, now we have looked at a diagram expression like psi bar psi phi. There is nothing to swap against, so there is no permutation factor over here. Okay, so when this guy goes into the Feynman diagram, this becomes minus I lambda d4z, this becomes minus I lambda d4z, and this becomes minus I g. Okay, so this was all terms with minus sign in the Lagrangian, and hence in Hamiltonian there becomes positive sign, and Hamiltonian times minus I is part of the rule. So here it is this d4z. Okay, now suppose I had minus lambda by 2, okay, phi dagger phi whole square, then what factor will sit in Feynman rules? Well, what I can write this as is some lambda minus lambda prime by 4 and phi dagger phi whole square, giving me minus I lambda prime into the Feynman rules, but lambda prime is nothing but 2 times lambda, okay, which is equal to minus twice I lambda. Here you can say lambda prime is twice lambda. That's how I wrote it. Okay. So you have to carefully put the denominator over here. So I could have written this 2 lambda by 4, okay, because the permutation factor over here is 4. So 2 lambda is my coupling that sits in my Feynman rules. Okay, in some of the models, when you do a computation, a single symbol will not come, may not come actually. So then when you have to write the Feynman diagrams, you have to look at which operator it's multiplying, and when I'm doing all possible contractions, what are the kind of symmetry factors one expects over there. So whatever that appears, you put that same downstairs, so that this will cancel, and whatever extra pieces that stay there will become part of the coupling, okay, like in this particular example. So this is another important stuff. So that's what we usually do, and let's move on to certain cancellations that we have been talking about. So coming back to two-point Green's function, this time ordered product of phi 1, phi 2, okay, these are all Heisenberg picture, I'm not writing that, and this is equal to 0 time ordered product of phi 1, phi 2, and this exponential thing, and 0 divided by 0 time ordered product of this exponential thing, 0. This is what I have, okay. And let me ask this question, that what is the denominator, okay. So denominator, if you just expand the first term, okay, so lambda, so again I'm talking about in lambda phi 4 theory by 4 factorial, okay, the same Lagrangian. So lambda to the power 0, I will have 0, 0, which is equal to 1, okay. 0 and 0 will interact, will contract and give me 1, because the first term is just this guy. Lambda to the power 1, I have minus I lambda by 4 factorial, and 0 time order product of phi, okay, there is also okay d4z, phi to the power 4 z, okay. So this particular guy is just 1, but this particular guy at order lambda, maybe I should not have equal to, but colon at order this, what do I get is a diagram like this, okay. That's it, nothing more. Now at order lambda square, so here all the factors blah 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 already included, symmetry factors, everything. So when I write a diagram over here, it's a true Feynman diagram. Unlike in the previous slides, when I was drawing the diagram, they were representative of only the propagators and nothing else. Here it is all the propagators, all the vertices, all the symmetry factors, everything, okay. When I write lambda square, then I have minus I lambda by 4 factorial square 1 by 2 factorial coming from the Taylor series expansion d4z1 d4z2 time order product of phi z1 power 4 phi z2 power 4, okay. And what this would be, it will be sum of several things. It will be a term like this, okay, but two of these guys contract independently, they have nothing to do with each other, okay. So this 4 z1s with each other and 4 z2s with each other. So here it was, just to say z, it was z1 z2. That's one thing. Okay, and here again I assume all the factors appropriately written using full final rules. Then I have a diagram which goes that between the z1 and z2 there has to be at least one link. So if I put exactly one link between these two, then this will be, z1 will be left with 3 guys to contract, z2 will be left with 3 guys to contract. Now 3 cannot contract among themselves, so another pair has to contract between z1 and z2. So this is z1 and this is z2, so I need this guy, and this contracts here, this contracts here, here is z1, here is z2. Now again I can't contract 3 of them together because one cannot contract with itself. Okay, so I have to contract 4 of them, all 4 of them. So here is z1, here is z2, and this is the diagram. So at order lambda square we have this diagram. Actually we don't need lambda square all the way, but let's just say this is my denominator. So I can just write diagrammatically 0 time ordered product of this exponential thing in the denominator as 1 plus this plus this plus this. So I will write brackets to indicate the same order thing. Plus higher order. So this is the guy sitting in the denominator. Right, now let's look at the guy in the numerator, and again let me see that I will do, so I drew some diagrams with more stuff, okay, for the 2-point function over here, and I jumped into the symmetry factor directly. So here I drew some diagrams, okay, and all the factors I was writing, because here I was trying to explain the factors. Now I will not draw all these factors, okay, and I'll draw the diagram with the numerator of this guy. Okay, so numerator of 2-point function is, so let me write it diagrammatically directly. So there will be a diagram like this when this is lambda power 0. Okay, lambda power 0 will have this, lambda power 1 will have this multiplying this bubble diagram, and remember this particular bubble and the bubble that came over here, this guy has exactly same expression. It's like this d4z, all these things, factors sitting over there, and these 4 guys contract with each other. Whatever factor will come over here, the same thing as if it is coming over here, because this x1 and x2 contracted with each other. So all the rules, all the factors that will make this 4 of the 5 contract with each other will be exactly the same. So this is one of the guy at order lambda, and then next thing will be that this x1 and x2 will be connected to this z guy. So these are the 2 diagrams I can draw at order lambda power 1. Now let's look at lambda square. What do I have? I have this diagram. Okay, here I'm first writing all those diagrams where x1 and x2 are contracted with each other and they are not contracted with any of the vertices, any of the interaction vertices. Okay, this is this, and among the 2 interaction vertices I can play the same game that I played in the previous page. When the order 2, all these 3 are there. Okay, so instead of writing them separately, I'll just write this, and I will write this, plus I will write okay, to order lambda square I wrote 1 term in the numerator. Okay, now I'll see that there is some, or at least one vertex goes with it's connected to at least one vertex, and or rather one vertex and not to the second vertex. Okay, so I will have a diagram where it connected to one of the vertex or this thing, and second one goes like this. Right, this is one piece, and there which is of order lambda because it's two pieces of lambda, and I can write a next guy, okay, where it has this guy, this guy. So both the vertices are connected. Then it has plus this guy and this guy. This kind of guy I can have, plus I can have this guy. Okay. So in this, so when two of them, both of them like is a okay. So let's do a counting of the components since we know the graph theory. So here is the diagram which is single component graph at lambda power 0. Lambda power 1, there is a graph which is two component because two disconnected components are there, and there is one connected component. At lambda square, the first guy is a 3 component guy, the second guy is 2 component guy, third guy is 2 component guy. Here this is a 2 component guy. Now afterwards it started to have 1 component guy, so everything is connected together. Okay. So up to order lambda square, how do I write the numerator? So let's write all of these. Okay, and what I will do, I will take this term, and the first term over here and write it like this particular guy is connected with 1 plus this is what this second piece will come, and plus okay, plus this is what multiplying this single propagator. Okay, so the first at order lambda, at lambda 0, at lambda 1, at lambda square, these are pieces. Now so I have, let me tick what all already did. So that's the first term, so I did this, and this entire bunch I did. Okay, now what is left among them, let me just tick them. I take this guy and I take this guy, okay, and draw them. So I have plus this order lambda already, and this is 1 plus, if I take this guy, okay, here I sit, plus order lambda square, I have plus and plus, okay. So these are the vertices. This is the various diagrams sitting in the numerator. The numerator is equal to this. Okay, now I ask this question that if I have to say that give me an expression for this 2-point function, this 2-point function over there up to order lambda square. Okay, so what I do, I have a numerator expanded all the way till denominator written all the way till lambda square, and numerator also written all the way till lambda square. Okay, so when I do numerator by denominator, okay, so what do I get? So first term is just this. Okay, so here I can itself write, that means this time ordered phi1 phi2 is equal to, when I take the ratio, first one is just this, because this order lambda square in the numerator and order lambda square in the denominator, they exactly cancel, and they are plus more terms, but I don't care right now. Okay, I did the expansion of both numerator and denominator to order lambda square. I'm taking the first term in the numerator and dividing by the denominator exactly, I get this piece. So this is the exact bubble cancellation that Kaushik Datta talked about. Next I come to this term. Okay, so this is already order lambda over here. Okay, so it is term lambda over here, so it's so this is, if I have to write this guy as a here, sorry, this order lambda prefactor is there and 1 plus this 8 factor is coming. So when I write a denominator for this guy, okay, so if I use the lambda square term in the denominator also, then that is, and then try to cancel it, then that is like including the lambda to the power cube term. But I want to do the computation only to lambda square. So there in the denominator itself, I have to make this approximation that I stop at the first two terms in the denominator, okay, because if I don't, then it will be higher powers, because it will have powers of this double eights and all these things multiply by the first piece over here, which is order lambda here, and something order lambda square will come here, with that will be lambda cube. We will keep those terms when we do a computation to lambda cube, okay. Then I will actually expand this to lambda cube and all this. Okay, so since that cancellation takes place, so I'll get a diagram like this up to order lambda square. So here order lambda square is approximation, followed by, when I have already terms of order lambda square in the numerator, anything other than 1 in the denominator will be higher order, okay. So I will write just this plus this plus this. So this is up to order lambda square is included, and then I'll say plus order lambda cube that are not included, okay. So this is basically the kind of approximations I made. Let me write it over here. So here 1 by a plus b lambda plus c lambda square, and here a plus b lambda plus c lambda square I had the first term, so I cancelled it. Second term I had lambda, because it's already, this thing is in terms of lambda, okay. So lambda d times 1 plus, rather not 1, a plus b lambda is what my expression over here, divided by, okay, divided by again a plus b lambda plus c lambda square. Now I have to ignore this c lambda square over here owing to this lambda over here, okay, because that's a higher order term, okay. So when I throw this out, or if I don't throw this out, I'll bring this. So okay, so let me just explain this term over here. It is lambda times t divided by 1 plus c lambda square divided by a plus b lambda. I can write it like this. When I do a small series expansion over this, so the very first correction will be lambda square times lambda, which is lambda cube. I don't want this, okay, because I'm doing computation only till lambda square, so this will be just lambda d. This is why this term is written as it is, okay. And beyond that, same thing, if lambda square is in the numerator, okay, then you just, in the denominator, you only keep order 1 only, and then this is your expression. And this is the kind of, at any order you can do this. You can go one order higher and you have this. You can go for any kind of diagram, okay. You'll always have scenario when your external vertices are not contracting with the interaction term that you put in. In that case, those interaction terms will contract with each other and will look exactly same with all the appropriate factors of the terms that we already have, the bubble terms that we have in the denominator. So this was a denominator bubble terms, right? So this is true for all of the any endpoint Green's function and any of the order that you want to do. So if here itself you wanted to stop at order lambda, what you would have done? You'll have first piece and you have this second piece coming over here, okay. The lambda square is ignored, okay. Then what you would have over here, just all these things here related in lambda square will not be there. So only 1 plus this 8 diagram, and the second piece just the 1, not the 8 diagram, because you only want to do it till order lambda. And since I want to do only till order lambda, then my bubble will also stop at 1 plus lambda, 1 plus this 8 diagram. Okay, and that will exactly cancel in the first case, and second case anyway I have to throw away the lambda this 8 diagram because that's higher order. It will give me higher order correction. So I will have only these two pieces, with appropriate factor, right? And when I went to the next order, I have another 3 diagrams. When I go to yet higher order, these exact will remain and more diagrams will keep on adding, because whatever things will come with prefactor over here, okay, will have exact same structure. Yeah, and they will cancel, keep on cancelling from the denominator if I take the appropriate order approximations. So at any given fixed order approximation, this is what is going to happen. Okay, so this is what I wanted to say about the diagrammatics and the symmetry factors. And yeah, so some homeworks and some I think some class test will be useful here before you hit the mid-semester exam. And so I suggest that the Friday class should be a class test. Okay, and I just want to mention that a couple of more results that one can write. It was actually written by Kaushik in his lectures, so I'm not going to write it again. You can just look at those things and all the exponentiation of the bubble diagrams that he has done. Proofs are there in Feynman, proofs are there in the Peskin book. So I'm not again going to talk about those. Next thing which will happen, if we are going to have a test on Friday, the next topic which will be introduction to the gauge interactions, both for fermions and scalar, that will happen on right after the mid-semester examination, week after from now. So that's all for this before the mid-semester. This was all the content. All 15 lectures, content of all the 15 lectures will be included in the exam, including the basic quantum mechanics and all those things, and all the, like, you cannot completely forget all the prerequisites. So I'm not going to ask you to make complicated proofs. If it is already available in the book, it will not be there in the take-home examination. The whole purpose of take-home examination is that I prepare the questions. Okay, and well, I'll take some hints from various places, but I'll prepare the questions. So next thing is we see you on Friday for the class test. Bye.